Hey, everybody. Another episode of THD Podcast coming to you. Dave Lindbergh from Hong Kong. And as always, we have our guest host on the technical side, Simon, calling in from Japan. Hey, Simon, how are you?
Very good, thank you. A beautiful day there, and it's a beautiful day here too.
All right. So a very special guest today, calling all the way from South Africa, Viljoen from Azoteq, who's a touch controller IC company. I think a very unique to have a semiconductor company in South Africa. So Viljoen,
Yes.
thanks for calling in and joining us today. We really appreciate it.
David, Simon, thank you. Thank you for the opportunity.
Okay, so maybe we could go to some slides and we could start introducing the Azoteq for the people watching, and we'll create some understanding on what your company does and where you've come from.
All right.
I thought that South Africa actually had a pretty strong background in semiconductor electronics design.
Not so much semiconductor, but we have a long legacy of technology in the 1970s and 1980s when we were isolated from the rest of the world. We established a pretty strong industry around military and security. And today, South Africa's and the engineering from South Africa is still world class in terms of security and things related to the security industry. So Azoteq's founder also comes from the security industry. In the 1980s and 1990s, he was involved with all kinds of different secure data transmissions that led to his previous company making their own ASICs. That was sold to Microchip in the USA in the mid-1990s. He came back to South Africa and then established a new company, but this time on the sensor side. So today, Azoteq is 20 years old. We're a fabless semiconductor company operating out of South Africa. We benefit from the relatively low cost of operations. So we still have a very good feed of world-class engineers coming through our universities.
Okay.
So that, along with the low cost of doing business in South Africa, actually put us in a very advantageous position to do what we do.
Okay. Hey, Viljoen, can you maybe put the presentation to full screen so that it centers better on the presentation?
Yep, of
There
course. There we go.
Okay.
All right, David. So can I jump into the slides, or you want to make a further quick introduction?
No. Let's get into it.
All right. So my presentation is centered around sensor solutions in the audio space, both for earphones as well as headphones. When I say sensors, let's call them hearables, there's various applications for sensors. One of the most obvious ones would be the user interface, either to touch them or to tap or to swipe, or some kind of user interface that is required, especially on the wireless and the Bluetooth hearables, where your phone or the controller is in a remote location and you just want to do a quick tap or a quick swipe on your hearable, either to increase the volume or skip a track or play, pause, reject a call, whatever. But there's secondary need for sensors. Azoteq has a portfolio of Hall effect sensors that are very useful for docking detection. And the capacitive sensing that we use on the user interface side is also very suitable for wear detection, which is important in the hearables. Okay, so a bit of an overview where the sensors are applicable in the hearables. In terms of the offering that Azoteq has, we do pure capacitive sensing ICs. Then we have a portfolio of modules. These can either be standard modules or bespoke modules that we design to the specification of the customer. And when I say specification, it is both the mechanical and the industrial design, as well as on the electronic side, what is required for this module. And then on the far right, you see something that we call ProxFusion. ProxFusion means it's a fusion of different sensing technologies into a single IC. So the little graphic that I have on the screen there is a chip scale package that's 1.5 millimeter in the long direction and less than a millimeter in the width. And that contains up to 3 or 4 different sensing technologies, all in this roughly 1 millimeter square IC package. So a lot of sensors that we can pack into a small space, which is very applicable, especially in the earphone space. So the most common application for a sensor in a hearable would be a single touch channel. A single touch channel would be most predominantly used for play pause, or to reject a call, or to take a call. Then we have a Hall rotation solution. We have, again, a very small chip scale device that can sense the rotation of a magnet up to 1 degree of accuracy. It's a small chip scale package. So let's say you want to make an earphone with the conventional rotation knob that is traditional in the audio industry. We have a solution for that, where you would put the magnet in the ear cup, and the rotating magnet can be sensed by stationary electronics in the rest of the housing. The nice thing about the Hall rotation technology is that it's a contactless technology. So for example, on the left-hand side of the earbud, where the stationary electronics are situated, that can be hermetically sealed from the outside. So you don't need any special grommets or sealing for the rotating part. So a very nice advantage for this rotation sensing, the fact that it is contactless. Dust and dirt can get into the ear, into the cap portion or the moving portion, without any detrimental effect on the sensing performance.
So it's almost like a mini gesture. It's a mini gesture control that is near the.
It's a mechanical rotation, David.
Okay.
So you will literally grab it between your fingers and rotate it like you would rotate a volume knob. So
Okay.
this is a pure mechanical movement.
Okay.
Then if we go to more channels, let's say your form factor is like the example I have on the screen. If you have a longer microphone boom industrial design, then it's very convenient to install something like 3 touch electrodes next to each other. Now, once you have 3 electrodes, you can do a lot in terms of touch gestures. It can detect a touch or a long touch, double touch or double tap, triple tap. But we can also detect swipes, swipe in the up direction, swipe in the down direction. So you see, by placing 3 electrodes on the microphone boom here, all of a sudden 5 or 6 or 7 different gestures open up to the user. So in a very small space, we can implement a lot of user interfaces. We can probably implement more user interfaces than what is practical, because at some point you will confuse the user. So you also have to limit it to something that is intuitive and makes sense. But again, a single chip can do all of that. The gestures are decoded on chip, so we literally just report a swipe up or a swipe down with a single bit that we are reporting to the master controller.
Okay.
Coming to wear detection, in the hearable space, there are 2 technologies to do, or 2 common technologies to do wear detection. One is optical, infrared, and the other would be capacitive. Now, with the infrared, you have certain disadvantages. First and foremost is the fact that you need an aperture. There need to be an opening in the housing for the light to be emitted and to received once again. That makes the industrial design cumbersome, and you also have to place the IR sensor exactly in the location where you have the aperture. So that's a pain for the industrial designers. If you go to a capacitive technology, it's very easy just to route the capacitive electrode into any small space. So you can have a piece of flex circuit that you route into a section of the earphone that is making good contact to the ear canal. So a very simple, from a mechanical perspective, a simple implementation, but from power consumption and cost, also superior to infrared. Azoteq has an added feature where we can track any changes in the environment. So let's say the earbud heats up or cools down, and there's certain drift in the signal. We can detect that drift with a reference channel, which means we can avoid any stuck conditions that happens due to the skin temperature heating up or something like that. So this is something that we matured over the years. The first generation of wear detection did not have this compensation for environmental changes.
Mm-hmm.
But these days we can do it pretty good and very robust.
Okay. Now, maybe you're going to touch on this, but are you able to use the same controller to have like maybe call receive, call answer, call reject type, several functions on a lead out to a controller touch, and then the lead go another lead for the wear detection?
Exactly,
Oh,
exactly. This is the power behind these Prox Fusion devices. This actually leads into the next slide. So it's the same device that I showed previously, a device that we call the IQS269. Now, this device has in total 8 capacitive channels, and it has on-chip Hall effect docking detection. So to give an example how to utilize this device, you can use 3 of the channels or 5 of the capacitive channels for the user interface. When you have 3 channels, already you can do a swipe up, swipe down, tap, tap and hold, double tap, triple tap. So 3 channels for user interface. You can deploy another 2 channels for this wear detection. One would be the actual wear detection and the other for the environmental tracking. And then the chip has a on-chip Hall effect sensor. The Hall effect sensor would be used to detect when you dock the pods in their charging case. So you will have a magnet inside the case, and the Hall effect sensor will detect once the pods are put in the case. So you put them in the case, and you can shut down other power-consuming circuits, for example, the Bluetooth radio or whatever the case may be. David, so all these functions are communicated over a I2C bus to the main controller. So we will generate an interrupt based on a predetermined condition. Either the swipe happened, or the dock happened, or the wear detection got triggered. And then the master controller can take a decision based on the signal received. If it's a swipe, you can increase the volume, or if it's a tap, you can play or pause the music, or if the wear detection indicates that the user took it out of his ear, then you can pause the music.
okay.
This is a small device. I spoke about the I2C interface before. The I2C gives a lot of flexibility because you have access to all the raw information. But in some architectures, the Bluetooth SoC is designed to interface with tactile buttons. Typically, your volume up, volume down in older designs would be on a tactile button. If the Bluetooth SoC does not support a I2C interface, we have a specific device where we emulate these tactile buttons on a GPIO. So we will decode the gesture on our side, let's say the swipe or the tap or the hold. We will generate a pulse that is then interfaced to the GPIO pins on the Bluetooth SoC.
Okay, very cool.
All right. As I go along, the features increase. So we have a part number we call the 626. This is a miniature trackpad. So now you see where before we just had a one-dimensional swipe interface, let's say up and down. Now we can have up and down and left and right. So more user interfaces open up in the same area. In this instance, what would be intuitive for the user would be forward and backward, typically to skip a track, and upward and downward to adjust the volume. And then again, the taps typically for play, pause, that sort of activity. These devices also have the wear detection and the on-chip Hall effect sensor. So again, all-in-one solution. In a very small, you see the ball grid array chip scale package on the graphic there. Again, around 1.5 millimeter by 1.5 millimeter big package.
Hey, Jean, what does it mean, the GPIOs, just on that last slide, the GPIOs do not require OTC initialization after power on reset? Is that
Simon, so typically when the whole system is up and running, there's an intelligent communication happening between the Bluetooth SoC and the touch IC. You can change parameters on the fly, you can change power modes. So very powerful once this I2C communication is established. But in the early boot up sequence, it takes a few hundred milliseconds for the devices to boot up. You don't have this communication going. But more importantly, there may be a stuck condition. So let's say your Bluetooth SoC is stuck for some reason.
Mm-hmm.
The only way for you to reset it is by interface on the touch interface. So it's a low-level communication interface to the Bluetooth SoC. So we will have something, for example, if there's a 5-second touch and hold, we will toggle a GPIO.
I see. So you can actually use that to power your Bluetooth on and off. Then.
Yeah, exactly. It's like a hard reset or a hard power cycle, something like that. A low-level communication where you don't need the master controller to be up and running at that point. Okay, force sensing is also something that's very applicable in the hearable space. Some of the advantages of the force sensing is the fact, again, that you don't need to find that very small tactile button because space is limited on the hearable. You can seal all your electronics hermetically, and it's often there's often criticism against tactile switches because you hear that annoying click in your ear when you press the tactile button. So this is the reason for the advent of force sensing in true wireless. With the same device using an inductive sensing technology, we can also do force sensing. Let me maybe jump. I think let me later dwell a little bit more on how the force sensing is performed. But in principle, you need a small inductive coil, either a trace on the PCB or it can be a surface mount component, where we generate an electric field. And if you have any minute movement of a conductive surface in the vicinity of that coil, it will change the inductance in the coil, and we can sense this with the IC. Again, these are standard part numbers from the ProxFusion family. So you will deploy 1 or 2 or 3 channels as is deemed necessary for this to make these inductive coils and to perform the force sensing. Again, can be combined with wear detection and Hall effect docking detection.
Okay.
So just to pick up on that point, because I'm curious about this. So the force sensing, you actually use an inductive change. Could you not do a similar thing with a capacitive change? So you close two capacitive plates by pressing on something. Is there an advantage to the inductive method?
Yeah. All right, Simon. So yeah, you're perfectly right. You can do it with capacitive. The disadvantage of capacitive would be the fact that it is prone to false activations. So maybe you just want to adjust the hearable in your ear, or you take it out of your ear. That can create a false activation when you put it down on the table. Because remember, the IC doing the capacitive sensing cannot distinguish whether it was a human causing this capacitive disturbance or whether it's something else.
Right. So static charge in the environment will equal the same effect as a mechanical change. I'll carry on. Whereas an inductor is not sensitive to kind of electrical disturbances from your body, static and things like that.
Exactly. And I think the most important one would be the interference from water. From a capacitive perspective, whether it's a human or whether it's water coming in contact with the capacitive sensor, the capacitive sensor just sees there's some change in capacitance. So capacitive sensing very prone to water, sweat, to cause a false activation. Whereas the force sensing actually requires a minute amount of physical movement. So you need to press it.
Okay.
What I'm proposing here is a variation on the force sensing. I said before that we have a technique for inductive sensing whereby we energize a coil. That coil can be on flex circuit or on a PCB. And then when any conductive material moves in the vicinity of that coil, we can detect that change in movement. So what I'm proposing on the screen here is to have an inductive coil on a PCB that is fully enclosed and fully sealed inside the hearable. We have a metal dome on the outside of the plastic, but there's no electrical contact. There's no galvanic or physical contact between the dome and the coil. From the user perspective, you can still press it like a conventional tactile button. You get that nice click feeling or the haptic feedback, but we take away all the hassles you have with sealing a tactile button from water and dirt, because that's the Achilles heel in the end for any tactile button. If water or dirt or corrosion get into the contacts, your contact is not working properly anymore. So this is a very, very nice solution to have a purely contactless, fully waterproof solution, but with the same user experience as a conventional tactile button.
Yeah, that's outstanding. I've done a lot of work in waterproofing of headphones, and always one of the challenge was the dome tack switch, and are they fully sealed or not sealed? And normally the brands would come to us after they've already designed it with the open tack switches, and then wonder why their products were failing. So this is a good way to start from the beginning and design it so that you don't have to worry about the penetration of the liquid or sweat.
Yeah. Oh, this is a very elegant solution, and it takes away a lot of headaches in both on the industrial design early on, but as well as on the manufacturing side. It just gets rid of all that sealing headaches that you have. Again, these devices, you will deploy one or two of the capacitive channels or of the sensing channels to do the inductive sensing. and the rest of the available channels can be utilized for something else like the wear detection, the Hall effect docking detection, or you can even make a combination. Let's say you want to do capacitive wear detection on the surface of the earbud, but you want a single tactile button, let's say for Bluetooth pairing or whatever, and that you can do with the inductive technique.
Fantastic.
All right, so let me just stand still, and this is kind of a summary. I spoke about the techniques all in their individuality. What we are proposing here is a sample of how these different technologies can be rolled into a single module. This is a single IC solution on a single module that is doing both force sensing, capacitive swipes, taps, tap and hold. It's doing capacitive wear detection and also the Hall effect docking detection. Now, David, I'm going to turn on my laser pointer. You need to show me whether this is working or not. Let me see. Is this working on your side with the laser pointer?
I can see your cursor. Okay, there you go. Yeah.
All right. Okay. So this will help a bit. All right. So the form factor is again the hearable with the microphone boom that extends from the pod. What we are proposing is to put this module inside the microphone boom. This is the design of the module. You have the chip scale IC in the central part here. The inductive coil is clearly visible. So in the assembly, the little flap you have on the left-hand side will fold over 180 degrees and be located over the coil. So once you apply a force to the cylindrical area, that little flap will move closer to the coil, and we will sense that change of inductance and decode that as a force detection. In the lower section of the, let's call it the pipe, we have 3 capacitive channels. Now with these 3 channels, we can detect touch, tap, tap and hold, double tap, triple tap, as well as swipe up and swipe down. So typically you can use that to adjust the volume. It's a very intuitive way to adjust volume by swiping your thumb up and down.
For the force sensor, what scale of movement are we talking about?
Simon, it's a function of how hard the plastic pipe is, but from the sensing perspective, we can very reliably sense down to around 2 microns of movement.
2 microns. Oh, that's incredible.
So to put that into perspective, the typical human hair is around 20 microns. So that would be 1/10 of a human hair. So it's just the slightest of deflection, but again, it's enough that water or putting it down on the table does not trigger it.
Mm-hmm.
The wear detection is a small electrode that's coming out on the right-hand side here. And then the Hall effect docking detection is done by an on-chip Hall effect sensor. So extremely small module, doing 5 or 6 different functions, all by a single IC.
Those are incredibly low current consumption figures.
Yeah. So that's the 3 microampere you have on there. It's at a relatively slow scanning rate. You will see 200 milliseconds. So we're taking 5 samples per second. Mm-hmm. Typically, when any interaction is detected, either a wear detect event or a swipe event or so, we will speed up the sampling, typically to 10 or 20 milliseconds of sampling, that you get a very good response. Mm-hmm. Then the power consumption would go up into the 30s or the 50s of microamps. but only for that short period while the user is interacting with the device. As soon as the interaction stops, we fall back to the low power sampling. And compared to the Bluetooth radio and the rest of the electronics, this becomes pretty insignificant.
Very insignificant. It's a thousandth of a.
Yeah. All right. I think that concludes my section on the earphones. I quickly want to run through headphones. It's much of the same. Here and there, something is different because now you have a larger area to work with and typically a larger area of interaction. Of course, all the principles that we discussed before holds for headphones as well, but we have one or two more opportunities in headphones. Okay, so on the left here, again, a small miniature module. I think we discussed a lot about that already. Then we do rigid gesture pads, typically going on the ear cup for gestures. But if you have a two-dimensional or a three-dimensional industrial design, instead of using a rigid board, we would go to a flexible board. And these flexible circuits are designed such that it can be laminated to all the inside curves of the headphone. So the one I have on the right-hand side, the purely round section, that would typically be for swipe and touch gestures on the flat section of the ear cup. And then the two wings that you see on either sides, that can be laminated into the perimeter of the ear cup. So you can literally grab your ear cup between your 5 fingers and perform a rotation gesture on the side of the ear cup, for example. But I have a better sample later on in the presentation. All right, so just talking about regular conventional gestures, we do the IC and we do the rest of the hardware. Azoteq prefer doing the whole module since it's a standalone subsystem, so we can control the outcome of and the performance of the gestures can be very well controlled. We support all the standard gestures, so typical swipes, 2-finger swipes, pinch, zoom, rotation, whatever the customer may require, we can implement it.
So if there's the customer has a slight variation in their industrial design for size, you could redo another PCB or flex PCB, and maybe the channel count is the same, but the pitch might change. So then you could just adjust the tuning slightly. Is that kind of customization possible?
Exactly. So we have a range of standard modules for customers that have relatively low production runs and don't want to invest in all the tooling and engineering. We have a range of standard modules in popular sizes. So that is just plug and play. We ship these modules with a adhesive already laminated, and they just stick them in. And then we have other customers where we do bespoke designs. So typically the customer would share his 3D files with us, and we design the module according to his specification. David, you spoke about changing the pitch or the performance or so. Very often we'll see the customer need to cut out a section, let's say for the Bluetooth antenna, or maybe there's a case where the industrial design is such that the headband cuts straight through the middle of the touchpad, but they need a certain kind of precision in a certain area. And we will adjust the pitch and the layout according to that to meet their requirements and to ensure a very good user experience.
Okay.
This is something that is unique from Azoteq. It's the fact that we can sense tactile domes, metal snap domes on a capacitive trackpad. We use a capacitive technique to sense these domes. So what this opens up is just another layer of user interface. let's say you want to use the touch for convenience features like volume or skipping a track. But there's some critical functions, either rejecting a call or taking a call, or for whatever you don't want a touch interaction, but you want a physical tactile interaction. We can combine both. So the touch performance is not impacted by the fact that we have these domes on the touchpad, but you can separate touch functions from physical, let's call them clicks or presses.
Okay.
I don't need to spend time on this. We spoke about the miniature trackpads. We do swipe up, down, all the gestures. We can even do a small rotation gestures on these miniature touchpads. Then talking about flexible circuits, the use of a flexible circuit opens up the option to go into any two-dimensional or three-dimensional shape. So let's say the picture that is proposed here. Typically, this would be a user interface that you use with your thumb. If you want to grab the whole ear cup and use your thumb as the user interface, we can make it as long as or as short as is needed and implement as many gestures. You can either separate certain zones for certain functions or just use any zone for a relative swipe up and down for one function, taps for another function.
Okay.
Now you see, if you extend the previous idea, if you extend it to a full 360-degree circle, if you laminate that electrode that is proposed in the picture there, if you laminate that to the perimeter of your headphone, now you can grab the whole earphone or the headphone ear cup between your 5 fingers, for example, and rotate it. Now, David, this is different than we had before. In the beginning, we had a mechanical rotation.
Mm-hmm.
In this instance, everything is stationary. Nothing is moving, and you just slide your fingers around the ear cup, much like you would have turned the knob on a conventional audio amplifier, but everything is stationary and you just slide your fingers around.
Yeah, very cool.
Right, and I think this is the last one. We also have the ability to make the touchpad either optically or acoustically transparent. So we can, you can call it drill holes into the sensing surface. And with these holes, you can either use it to display kind of backlighting, or otherwise make it acoustically transparent. So if there's a case where you need to have your speaker driver behind the user interface, we have the ability to open up a certain area, let's say up to 30 or 40% of the touch interface can be opened up, either for sound or for light, to be transferred from the back to the front.
Okay, that's pretty clever.
Yeah. So, gentlemen, I think this is it from my side. The idea was really to open up ideas of what can be done with Azoteq sensors, break down some of the restrictions that exist on industrial designers. We spoke about stuff like the waterproof tactile buttons, or something where the touchpad can be acoustically transparent. All of these are ideas just to create more freedom for the industrial designer. And also on the electronic side, if you need to condense a lot of functions into a very small area, either on chip level or on module level, we can make these extremely small. I have a few samples here. I'm not sure how well my camera will focus on these.
Yes.
This is that module we discussed. So you see the coil. So the coil would be used as the force sensor. We have the small flap that will fold back over the coil. So this would be your force sensor, this small little flap moving. The 3 electrodes you see on the bottom, these would be the swipe and the touch interface. The little flap I have on this side would be the wear detection. So that would be routed into the earbud to an area where it makes good contact with your ear canal. And then the Hall effect sensing is done on chip. So extremely small with a lot of functions condensed into a small space. This is a guy where we combined the, you see this is a conventional diamond pattern for touch gesture inputs, but you also see the coil next to it. So in this instance, I have a 3D printed example here. So in this instance, you can have the touch interface on the cap of the earbud, but we can also have that waterproof inductive button on the side. Let's say you want to use it for Bluetooth pairing or whatever. And then this guy also has the wear detect, different functions, all condensed into a small module that can fit into the into, let's call it a typical form factor for the earbud.
Very good.
I've got a couple of questions, if you don't mind, sort of into some nitty-gritty stuff.
Yeah,
for the most part, it's communicating over an I2C bus. Is the device a master or a slave?
It's a slave, Simon.
How do you know to get the data out of the slave?
So typically it's a 3-wire I2C. We will generate an interrupt based on a predetermined event. So the architecture is such that the master controller can also go to sleep if he wants. So you can send the master to sleep and set up a predetermined event to wake up the master. We will generate the interrupt based on this event. And then the master will check the status register and it will see, all right, the flag is set for swipe up or swipe down or whatever event occurred.
So typically you're just going to read one register, one byte?
Typically, you have access to all the raw information. So if you want to decode, let's say you want to decode your own gesture on your master. For some reason you want to do your own gesture. You have access to all the raw information. But if you don't want, you literally need to read the first register in the memory map, and there will be a flag set telling you it was a swipe up or a swipe down.
Okay, excellent. So the processor in there is setting these registers. Is that a predefined, a fixed setup, or is there a way to configure those?
It's a fixed setup. So you can adjust certain parameters like either a threshold or a sampling frequency, something that is frequently required to adjust by our users. But for the rest, it's a fixed ROM. And other than adjusting your threshold or some user functions, we take care of the rest, and it's not open to the master.
So those parameters that you can adjust, for example, you mentioned threshold, etc., are they in volatile memory or are they persistent?
It's volatile, yeah.
So you would actually store that on your hosts if you have some flash or something, and then just write that out each time you boot.
Exactly. So these parameters are determined at design time. You will say, for example, you need a 10% threshold on your touch or whatever the case may be, and you will set that in your master. And every time it boots up from a cold boot, you will write those thresholds down to the slave device.
So when you design a product, there's a calibration process that you would go through to determine these things?
We need to distinguish between the design activity. You set up these thresholds based on your design. So it's a function of the size of the electrode and the thickness of the plastic, and let's say the wear detect electrode, how close that is going to get to the ear canal, what sort of thresholds are required. But the device itself, when it powers up, it calibrates itself to the optimal position. So if there's small manufacturing tolerances, or let's say humidity or heat or whatever environmental changes, or even if, let's say, your adhesive starts to deteriorate over time or something like that, every time the device powers up, it will recalibrate for that. And then your master writes down the specific threshold that was determined during design time.
Right, got it. And so you're offering a lot of modules. Does that imply that designing the capacitive part on a flex PCB is quite a difficult thing? Is that quite a specialist field?
Simon, when the module is a subsystem, let's take the case of the headphone. Usually the touchpad would be a standalone system. You will have your main board with the master controller and the DSP and the Bluetooth radio, and the touch is a standalone system. Then we prefer making the whole module and actually manufacturing and shipping the module, because we can control everything. Our factory is set up to perform the testing, and we make sure when we ship these modules, they are fully qualified, 100% tested. So you don't have any yield loss on the incoming side either. But if the design is intricate and our IC is only a component that is part of a larger subsystem, for those customers, we just supply an IC. All right, so there's the option to buy a module if it's a standalone subsystem, or otherwise, if the sensor is part of a more complex system, we will only supply the IC. But then in those instances, we collaborate with our customers and help them with the layout. We have the experience to help them avoid certain pitfalls and just shorten the design cycle, that they don't need to go through 3 or 4 iterations. We give them the tips right from the beginning, and they get it right normally on the first or the second time.
So there's also a GPIO version you mentioned, and that setup could actually be just a drop-in swap for tack switches, essentially.
Exactly. That was the whole purpose. That's how the device was conceived. For the lower end Bluetooth SoCs, they typically have 3 or 4 GPIOs where you would interface your tactile buttons, and we emulate those functions. So we have the touch sensing on one side, we decode the gesture, and we emulate that on a GPIO.
So in that case, is it reasonable for somebody to say, I've got a board that has some buttons on it, and I just want to replace those buttons with essentially a metal pad? Is that a doable thing? Is it at that level?
Yeah. Exactly. Yeah.
Perfect. Okay, I think I'm ready to go.
Cool.
What sort of water quantity do you require?
The ICs are shipped in reels of 3K.
Mm-hmm.
So, but you can, they are sampled through popular online distributors as well.
Oh, right. So I can buy some off
from the online guys. You can get 10 or 20 pieces from the online guys. And then we have the large volume distributors that will ship you the MP quantities. We also have evaluation kits. So every single device has its own evaluation kit. And we have a USB translation dongle. So if you buy the evaluation kit and the dongle, you get a PC development or a laptop environment where you can see all the sensor information in real time. So you can have while you're designing, you can literally get your eyes on how the sensor is performing, what the sensitivity is, what the noise levels are. So a very friendly development environment.
Fantastic.
Okay.
Fantastic.
So yeah, we can put some links in the description below for not only Celtec's contact, who's one of the people that kind of introduced me to Azoteq at the beginning, but also the contact details for Azoteq directly. So I guess that's if there's anything else, Jean, that you want to add before we say goodbye.
David, no, thank you. Thanks for the opportunity. And yeah, I hope for your audience, I could open up their minds a bit and break down some of the existing limitations that exist. We have very nice solutions. I think it's very innovative. So yeah,
I, yeah, I definitely think you guys are one of a kind for non-display touch user interfaces for headphones and audio speakers. But it goes a lot further than that. Maybe some other day we can come back and talk about all the other applications. But I think audio's done pretty in depth today. So I guess I just everybody likes what we're doing. Please hit like and subscribe. And very special thanks to Simon for calling in from Japan. And a very warm thanks to Jean calling in all the way from South Africa and telling us about Azoteq today. We appreciate it.
Thank you, gentlemen.
Okay, thanks. Bye-bye, everybody.
Bye-bye.